Now from this beams layout, we want to show the effect of inserting plinth beams where it was not included in the structural drawing. We will do two calculations. The first, to show the total load on the column when there is no plinth beam. Then we also show the effect when plinth beams are introduced. Now from the drawing, you will see span AB, that is the distance from A to B is 4 meters, then B to C is 4 meters as well. So meaning that on the x-axis, we have two spans of 4 meters, whereas the vertical grid B, we have 3 meters, 3 meters. Now, before we start our calculation, we want to determine the area, which we call tributary area. That is going to be 4 multiplied by 3, which is 12 meters squared. Then we'll do same for the contributory span or girth. That's the total distance or length that contributes to the load on this column. Now, span AB, you can see is 4 meters. So half of that span takes load to this column, whereas the other half goes to the column on the left. Then from that column to have the span on the right also takes load. So now this distance is, this span is 4 meters. If you divide 4 meters by 2, you have 2. The same thing this way. So total distance there is 4. The same thing on the vertical distance. So we have half of 3 plus half of 3, which is 3 also. So we have 4 plus 3 as the total distance that contributes load on this column. So we've established that. Then I have stated the various parameters here. 1, the thickness of the wall is 225 millimeters. We're using the limit state design. That is according to BS 8110 part 1 of 1997. Then the building, the intended use, we assume is a residential building. So that means the live load we use here is 1.5 kilonewton per meter squared. Then the structural element that we are going to design is the pad footing at that column point, that is at point BE. Then the roof load is 1.5 kilonewton per meter squared. Then the slab ultimate load is 10.52 kilonewton per meter squared, whereas the specific weight of concrete is 24 kilonewton per meter cube. Then that of block is 15.42 kilonewton per meter cube. Then we will apply the basic factors of safety. So for GK, that is dead load, is going to be 1.4. For live load is 1.6. That's according to BS 8110 that I stated. Then for roof load, we apply 1.5. So let's start from the roof now. To get that roof load, we have 27 kilonewtons. Now, how do we get it? It is simply to multiply the roof load, which is 1.5 by 12, which is the area. That's the area of the roof that contributes load to this column. Then we apply the factor of safety 1.4, so you have 27. We do a similar thing to roof beam to have 15.88. That is the concrete density times the total volume of concrete in the beam that contributes load to this. Then we apply the factor of safety 1.4. Then for column, you know, the headroom is 3 meters. So we multiply that 3 meters by the lateral dimensions of the column. That's 0.225 times 0.225 times 3, then multiplied by the specific width of concrete, which is 24. Then we multiply by the factor of safety. We have 5.1. Then we have column on the ground floor. Remember, that is column on the first floor, connecting the first floor slab to the roof. Then we do same to the column on the ground floor. We have the same 5.1 kilonewtons. Then for wall, this is our major consideration now. Let me take time to explain that, but it follows the same process. The total distance that contributes load on this column, we said is 7 meters. So we multiply that 7 meters by the height of the wall, which is 3 meters. Then we multiply it by the width of the wall, or thickness of the wall, which is 0.225. Then multiplied by the specific weight of blocks, which is 15.42 kilonewton per meter cube. So we now have a total of 102 kilonewtons. Then for slab, the ultimate design load for slab is 10.52 kilonewtons per meter squared. So we simply multiply that by the area, the tributary area, which is 12. Then no need to apply factor of safety because that has been done already. Remember, we had calculated from the finishes, loads from finishes, load from self-weight of slab, then load from partition, light partitions. So that's how we had this 10.52. We had done the 1.4 by GK, which is dead load, plus 1.6 by QK, which is live load. So that's how we had the 10.52. So we multiply that, like I said, by the area to have 126.24 kilonewtons. Then the weight, the load from the first floor beam. So a total of 305 kilonewtons. Now, if we use that to get the base, to calculate the base, assuming that our soil bearing capacity is 120 kilonewton per meter squared. So our footing is going to be 1.4 meters by 1.4 meters by 0.3 meters. Then for reinforcement, it will be Y12 at 200 in both directions. Now let's do the same calculation. We're going to use the same thing, but this time around we're going to insert the plinth beam. So the plinth beam, let's take it that the depth is 300. So if you multiply the concrete density, which is 24 kilonewton per meter cube, by the lateral dimensions of the beam, that is the total length, which is 7, multiplied by the thickness 0.225 by depth 0.3. Then you now multiply it again by the factor of safety, which is 1.4. So you will have a total of 15.88 kilonewtons. Then for wall, it's the same thing as what we had. You know, it's the same headroom and the same span. So 1.4 times block density, that's the specific weight of block, which is 15.42, times 4.73, we'll have a total of 1.03. So if you add the two together, that is the weight of the wall load, plus the beam load, that is plinth beam load, that is 102 plus 15.88 kilonewtons. What we have is 118 kilonewtons. That is much. That is much. So that is the same thing as 12,000 kg. 12,000 kg. Now 12,000 kg is about 240 bags of cement. But remember that one bag of cement is 50 kg. So precisely we have about 241 bags of cement. That is the weight that you now bring onto one column as an additional load outside the other 305 kilonewtons that we had. So if you now add this 118 kilonewtons to 305 kilonewtons, we're now going to have 423 kilonewtons. Now let's use that 423 kilonewtons to design this same footing using the same bearing capacity of 120 kilonewton per meter squared. So what we're going to have is 1.7 by 1.7 by 0.35 as the dimensions of the base. You can see the clear difference. When we did the other one, we had 1.4 by 1.4 by 300. So this time around, the base has increased by 300 in width. Then this way too, by 300, you have 1.7. Then even in thickness, the other one without plinth beam was 300. Whereas in this one, it is 350 millimeters. Of course, you know what that means, to be repeated in the various column points all around. You can see what that can cause. I'm even not even emphasizing on the waste of materials. No, that is not the concern. But the overboard we've gone. The design by the engineer said 1.4. Now you're creating a scenario where it should be 1.7, but you still maintain the 1.4. And it don't end in the lateral dimensions of the pad footing. We also talk about the reinforcement. Here it requires Y12 at 150 mm both ways, whereas the other one was supposed to be Y12 at 200 mm both ways. So you can see the clear difference. So it's not a joke, it's not something we can think of. So structurally, it is bad. Then economically, it is bad. This is something we could have avoided if we had allowed the building to remain the way the engineer had designed without the plinth beam, because this ground floor level, like I stated in my previous video, would have rested on the soil. But this time, with the introduction of the plinth beam, just like I've shown in this drawing, so you can see that from here, see it, from this column to here, you take that to this column, then from here, halfway here to this column, halfway here again to the column, halfway. So you have a total of 7 meters. Then with the height. So please, it's not a joke. It's not something we assume that we can do. The engineer knows better when it comes to structural stability and strength. So we need to stick to what the drawing says. But like I always say, if there is need to introduce any element, just go back to your architect. Then the architect will discuss with the engineer. Then these things will be resolved first on paper. Like I've explained here, or I'm explaining here, it's on paper. It's easier here. It's cheaper here. It's not a guesswork, not by assumption. So here in engineering, we believe in mechanics. So we'll talk about the structural mechanics first, then structural design. It's a very serious matter. In fact, with what I've done here, which from the video you're going to see, even the formula I want you to have, but it's not as light, it's not as short as what I only tried to make it brief, to make it a little interesting. So in conclusion, you can build without the plinth beam. The plinth beam is only necessary, or should only be included in a structure only if the engineer had designed for it. But if not, please allow that structure to be.